Hello students, I am Dr. Krishna Kumari, Assistant Professor in the Department of Mathematics at SRM Institute of Science and Technology. Today I am going to present a topic from Probability and Statistics titled Statistical Control Charts. Statistical control charts are one of the most important tools used in quality control and process monitoring. They help us understand whether a process is stable or if there are any unusual variations that need attention. This topic has wide applications in manufacturing industries, healthcare systems, service sectors, and even in data analytics, where consistency and quality are very important. In this presentation, I will explain the different types of control charts, their formulae, and when each chart should be used. Let us begin with an overview of different types of control charts. Control charts are mainly divided into two major categories, a variables chart and attributes charts. Variables charts are used when the data we collect is continuous or measurable. For example, measurements such as height, weight, temperature, or length fall under variables data. On the other hand, attributes charts are used when the data is discrete or count based. For example, counting the number of defective items or the number of errors in a process falls under attributes charts. So here under the variables charts, we have X bar chart, R chart and S chart. And similarly, under the attributes charts, we have NP chart, P chart and C chart. Each of these charts have a specific purpose and choosing the correct chart depends on the type of data we are working with. Now let us understand the classification more in detail. Variables charts are used to monitor processes where data is continuous. The X-bar chart is used to monitor the average or mean of the process. It helps us understand whether the process is centered correctly. The R chart is used to monitor the range, which is the difference between the maximum and the minimum values in a sample. So it shows the variability in the process. The S chart is used to monitor the standard deviation, which is another measure of variability. It is more accurate than the range, especially for large sample sizes. So together, these charts help us understand both the central tendency and the variation of the process. This is important because a process may have a correct average but still have too much of variation which is not desirable. Now let us look how these control limits are calculated for these charts. The central line of CL which represents the average, and similarly the upper control limit is denoted as UCL and the lower control limit as LCL. So these limits define the acceptable range of variation in the process. For the X bar chart, the central line is the overall average of the sample means. The upper and the lower limits are calculated using constants and average range. And for the R chart, the central line is the average range and the limits are calculated using constants such as D3 and D4. For the S chart, the central line is the average standard deviation and the limits are calculated using the constants B3 and B4. So the key idea is that these limits are based on statistical principles, typically using three standard deviations from the means. So if any data point falls outside these limits, it indicates that the process is out of control and requires investigation. Now let us move on to the attribute chart. Attribute charts are used when the data is based on counts rather than measurements. The NP chart is used to monitor the number of defective items in a sample when the sample size is fixed. The P chart is used to monitor the proportion or fraction of defective items and is suitable when the sample size varies. The C chart is used to count the number of defects in a single unit or item. So it is important to understand the difference between a defect and a defective item. A defective item is one that is completely unacceptable, while a defect is a flaw within an item. So one item can have multiple defects. Now let us just look at the formula used in these charts. For attribute charts, control limits are also based on statistical distribution. For the NP chart, the central line is the average number of defectives and the limits are calculated using the standard deviation formula for binomial distribution. For the P chart, the central line is the average proportion defective and the limits depend on both the proportion and the sample size. While for the C chart, the central line is the average number of defects and the limits are based on the Poisson distribution. So in all these cases, we use 3 sigma limits, meaning plus or minus 3 standard deviation from the mean. So this ensures that most of the data points fall within the limits if the process is under control. So if points fall outside these limits, it indicates an abnormal variation in the process. So far, I'm sure that I have given a clear idea about the basics of statistical control charts and about their control limits. So now let us move on to the problems of the different types of control charts. So the first problem is based on mean and range chart. So according to the problem, given below are the values of sample mean and sample range for 10 samples, each of size 5. Draw the appropriate mean and range charts and comment on the state of control of the process. So before finding the control limits for the given problem, first we should find the grand mean and the mean range of the given problem. The given problem has 10 samples with a mean of 530. So the grand mean is going to be 530 divided by 10, which is 53. And also the given sample has a range, total range of 60. So the mean range is going to be 60 by 10, which is going to be equal to 6. So as we have seen the formula for the control charts, so from the formula, the central line value is going to be equal to the grand mean, so which is going to be equal to 53, and the lower control limit for the mean chart is going to be 49.54, and the upper control limit is going to be 56.46. Similarly, for the range chart, the central line is going to be the mean range, which is 6. The lower control limit is going to be 0, as well as the upper control limit is going to be 12.69. So this is going to be the final graph of mean chart and R chart. So from the mean chart, we can see that sample 2, that is which is of mean 58, actually lies above the upper control limit, and sample 6, that is which is of mean 46, and sample 3, that is of mean 48, lie below the lower control limit. So since these samples are not lying within the control limit, the average of the process is obviously conserved. Therefore, the process is not in control for the mean chart. Whereas in the range chart, all the 10 sample range points lie within the control limits. Hence, as far as the variability of the process is concerned, the process is in control. So, according to the mean chart, the process is not in control, and according to the range chart, the process is in control. Therefore, we come to an overall conclusion that the process is out of control because both the process should be under control. Since one of the chart is not under control, we come to an overall conclusion that the process is out of control. Now let us go to the next problem, that is based on mean and standard deviation chart. The values of sample mean and sample standard deviation for 10 samples are given and each are of size 4. And it is mentioned that they are drawn from the production process. So they have asked us to draw the appropriate control charts for the process average and process variability. And they have also asked us to comment on the state of control. According to the formula that we have already seen, the grand mean is going to be equal to 196 by 10 since 10 samples have been given. So it is 19.60, and the mean standard deviation is going to be 33 by 10, which is going to be equal to 3.30. And also we have to note down the constants from the control charts. So the constants, since they have mentioned the sample size is equal to 4. So according to the sample size, that is n equal to 4, the constants A1 value will be 1.880 and the constant B3 value will be 0, as well as the constant B4 value will be 2.266. So we have already seen the formula for the control limits. So according to the mean chart formula, the central line is going to be equal to 19.60, the lower control limit will be equal to 12.44 and the upper control limit will be equal to 26.76. And similarly for the standard deviation chart, the central line will be equal to 3.30. The lower control limit is going to be equal to 0 and as well as the upper control limit is going to be equal to 7.46. So here I have shown the calculations how I have got this value. So I have just applied the formula and I have shown the calculations how I have received these values. So from these values, this is going to be the final mean chart as well as the standard deviation chart. So from the chart, it is visible that in the mean chart, all the 10 sample mean values, that is they are ranging from 16 to 23, lie within the lower control limit as well as the upper control limit. Therefore, the process is under control. Similarly, when we just note down the standard deviation chart, all the 10 standard deviation values lie within the lower control limit 0 and the upper control limit 7.48. Therefore, the process variability is also under control. Therefore, we come to an overall conclusion that the process is completely under control with respect to both average and variability. Now,
So
let
since
us move
each
on to the
sample
next chart,
contains
that is
50
NP
items
chart.
and also the number of
In a
defectives
factory
are
producing
given,
electric
the
bulbs,
appropriate
the
control
number of
chart for the
defectives
given
found in
problem
the
is going to be
inspection of
NP
10
chart.
lots of 50
So
each is
totally there
given
are
below.
10 samples
Draw
and the
the
total
control
number
chart
of
for the number
defectives
of
is going to be
defectives
50.
and comment on the
Therefore,
state of
NP is going to
control.
be 50 by 10, which is 5. And from the value of NP, we can calculate the value of P, which is going to be equal to 0.10. From the above values, we can find the control limits for the NP chart according to the formula. The central line is going to be NP, which is 5, and the lower control limit is going to be minus 1.36. So we cannot use any negative values while drawing the control charts. Therefore, we consider the lower control limit to be 0 and the upper control limit is going to be equal to 11.36. So from the given values, we can draw an NP chart, and from the chart it is visible that all the sample points lie between the upper and the lower control limits, that is in between 0 and 11.36, and therefore the process is fully under control. So our next problem is based on P chart. So according to the question, 10 samples of 150 items each were drawn from the output of a process. The number of defective items in the samples are given below, and they have asked us to prepare a control chart for the fraction defective and comment on the state of control. So totally the sample size is 10 and they have also given the number of defective items in the question. So according to this question, the appropriate chart is going to be P chart because they have asked us to find the fractional defective. So the total number of defective is going to be 140. So from 140, we can calculate the NP value as 14 since it is going to be 140 divided by 10. Therefore, P value is going to be equal to 0.0933. Approximately, we can consider it as 0.093. From the formula of control limits, we can calculate the control limits for P chart. So before calculating the control limit for P chart, first we have to calculate the fractional defective values, which is nothing but NP by N for each sample. So we know the value of NP as well as N. So from that we have to calculate the P value. After calculating it, we have to calculate the control limit points for P chart, which is nothing but the central line is going to be 0.093, which has been already found out, and the lower control limit is going to be 0.022 and the upper control limit is going to be 0.164. So from all these given values, we can draw the graph of the P chart by using the fractional defective as the y-axis and the sample number as the x-axis. So from the chart, it is evident that all 10 sample fractional defective values lie between the lower control limit and the upper control limit, and here no point falls outside the control limits. Therefore, the entire process is under control. So this is going to be the last type of our control chart, that is the C chart. So let us move on to the problem. 10 electronic circuit boards were examined for quality control test. The number of defects in each circuit board is recorded below. Draw the appropriate control chart and comment on the state of control. So since the number of defects per sample containing only one item, that is the circuit board, we are going to draw the C chart for this question. So the total number of defects is going to be 40. Therefore, the value of C is going to be 40 divided by 10, which is 4. So the entire control limits for C chart is going to be that the central line is nothing but C, which is 4. The lower control limit is going to be minus 2. Since the lower control limit can't be negative, we are going to consider it as 0, and the upper control limit is 10. So from the given values, draw the C chart by using the number of defects as the y-axis and the unit number as the x-axis. And from the given chart, that is the graph, it is evident that all 10 sample points lie between the lower control limit and the upper control limit. No point falls outside the control limits. Hence, the entire process is under control. Now, let us summarize the key points of this presentation. The X bar and R chart are used for continuous data and help monitor the mean and variability of the process. The X bar and S chart is an alternative to the R chart and provides better accuracy for larger sample sizes. The NP chart is used to count the number of defective items when the sample size is fixed, and the P chart is used to monitor the proportion of defective items and works well when the sample size varies. The C chart is used to count the number of defects per unit. So an important rule to remember is that if the lower control limit becomes negative, we set it equal to 0 because counts can't be negative. Overall, control charts are very useful tools for detecting variations and maintaining quality in any process. So with this, I conclude my presentation. Thank you for your attention. Thank you all.